Yeah, so hello everyone. So welcome to the TA session for the second week. Um, this week, we are supposed to implement a 4-bit binary for adder and subtractor. So this is a similar problem as the 12th question of your second assignment. So I suppose you have already done that assignment. So what's the difference from the lab for the last week? In this lab, in addition to the original adder, we are supposed to implement a subtractor on the same hardware. So your design should have two main functions, add and subtract. Those two functions are selected by a select signal. You can implement it in your switches. So I will first very briefly introduce binary subtraction. Uh, you may already learned from your lecture. So the idea of two's complement numbers. So a minus b equals a plus negated b, right? And that equals a plus bitwise naught of b plus 1. So the bitwise naught is to flip every single bit of b. Let's see an example. So 5 minus 4 equals 5 plus negative 4, and that equals 5 plus bitwise naught 4 plus 1. Yeah, so you can go through this example. Firstly, we flip every bit of 4, and we add 1 to that result. And finally, we add the number 5 with the result. So we get positive 1. So why do we need that additional 1? Because you can manually check it using two's complement numbers. The absolute value of, for example, positive 1 and a negative 1. If you just flip it, the absolute value will change for 1. Yeah, that's why. So how can we implement that additional single 1? So that could be simple, right? We have a spare carry-in bits at the adder. So whenever we need that additional 1, we use the carrying bit to add 1 to the whole adder. Okay, but if it's a plus b, we do not need it, so we need to select it. Now comes a question. So how should we do the bitwise NOTs to operand b? So here I have found out two examples. The first one, we use a multiplexer. For here, y0 through y3 are the digits of operand b. So firstly, we use 4 inverters to invert each of the bits. Now we have both the not inverted original b and the bitwise inverted b. We have 2 copies. Then we use a multiplexer to select from these 2 signals. Okay, you can also see the carry-in bits is also depending on the select bits. This is the first implementation. We need inverters as well as multiplexers. Now it is a second implementation. We do not need a multiplexer, but we have an XOR gate. When the select bit equals 1, that is, we are doing subtraction. We do the XOR gate has one input set to 1, and that XOR gate can flip each bit of B. Why? Let's see. Because this is the calculus of the XOR gates. So let's suppose the original signal is A. If A XOR with 0, the output of the XOR gate keeps unchanged. It's still A. But if A XOR with 1, then the output of the XOR gate has been flipped. It becomes not A. So that's why we can flip it. Okay. In addition to the other subtractor, we will implement 4 more functionalities. They are overflow detection, zero detection, prime number checking, and parity checking. So we will go through it one by one. The first thing is the overflow detection. So there could be other ways to implement this if we have access to the internal signals of the IC chip. But the problem is, as you may already know, the IC chip is a package. You cannot probe the intermediate signals of the adder. So we only know the inputs and outputs of the adder. So how do we know the adder has an overflow? So I will just show you the results, and you can manually check it after the lecture. So actually, an overflow happens if the most significant bits of A and B are equal, and that A or B most significant bit is not equal to the sum bits at the most significant bit. So for example, if A4 and B4 are both 0, but their sum is 1, the fourth bit of the sum is 1, it means there's overflow. Or A4 and B4 are both 1, and the sum bit is 0, there's overflow. So for here, A and B are the direct inputs of the adder. So it's not your direct operand, because for subtraction, you are flipping B, right? So this is the result after the flipping. Second functionality is zero detection. It's quite simple. So the zero detection should be set to 1 if all the sum bits are set to 0. So all the sum bits are equal to 0. Number checking. Basically, it just checks the prime number within the range of all legal numbers. So I have manually do the simplification using Kmap, and here is the result I can show you. So, but in your lab report, probably you should manually write down how you compute this formula, or you prefer to do the computation by yourself and you get a different formula from mine. It's also fine as long as the result is okay. And the parity checking. So parity means the sum has all the number of ones. So we have 4 digits in a sum. So the parity, you are supposed to check whether or not there is an odd number of ones among them. So the formula is you XOR all the bits, and if the result is still 1, that means there's an odd number of ones. You can manually check it. You can plug in S0, S1, S2, S3. Yeah, you can manually plug in it, and you can check. Okay, so this lab is quite an open. You can figure out ways by yourself to do all the implementations. I will not give you a fixed solution, but I can give you some suggestion how you can implement this design. What components do we have? So we have NAND gates, which is an AND gate, and the output is negated. And NOR gates, which is an OR gate that the output is negated. Inverters, which is just a simple negation. AND gates, OR gates, XOR gates, as we have mentioned. And a multiplexer, which is a two-way selector. So you have an selecting signal for the multiplexer, and you select, and the output of the multiplexer is selected by your selection signal from the two inputs. Okay, let's go through it very quickly. So you have a chip which contains 4 copies of NAND gates, and a chip which contains 4 copies of NOR gates, and the 6 inverters, and the 4 AND gates, 4 OR gates, 4 XOR gates. And this is 4 two-input multiplexers. Yeah, you can read my instruction to see how it works. So you have 4 multiplexers.